number 13 of transport phenomena in mesoscopic and nanoscopic systems. Last day we were discussing about nanotubes, and we discussed that there are three kinds of nanotubes. One is known as zigzag nanotubes, where the axis of the nanotube, or the axis of the hollow cylinder of the nanotube, is in this direction, and the circumferential axis, that is the direction forming the circumference of this nanotube, is in this direction. So this surface of the nanotube is basically exposed or remains uncovered. Okay. The second type of nanotube is known as armchair nanotube, where the axis of the hollow cylinder of the nanotube is in this direction. Okay, so this one is the axis of the hollow cylinder of the nanotube, which we call T, and the circumferential direction, that is the direction along which the circumference of the hollow cylinder forms. This is basically along this direction. So basically this kind of surface is exposed for the nanotube, and this surface, not surface but line, since this line looks like an armchair, this kind of nanotube is known as the armchair configuration. And then there is a chiral configuration of a nanotube, where the axis basically is kind of arbitrary. So the circumferential axis would look somewhat like this, and the axis of rotation is basically the axis of the hollow cylinder of the nanotube is basically perpendicular to this direction. So this is our axis of the hollow cylinder of the nanotube, and this is the direction which forms the circumference of the nanotube. Okay, and last day we also saw these two formulas, that the circumferential axis is given by this vector, where m and n are basically integers, and when the wave function basically completes one loop around the circumference of this nanotube, the wave function should go to its former value, or the phase of the wave function should go to its former value. So this is, let us say, the cylindrical structure of the nanotube. So whenever the wave function just moves, let me use a different color. So whenever the wave function basically moves starting from this point, it goes here and it again returns back to this point, it should be at the same phase. Otherwise it would cause a destructive interference, and that wave function cannot exist inside the nanotube. So only those values of wave function would exist inside the nanotube for which this dot product should be an integer multiple of 2 pi. Okay, so this is an integer. So if you don't understand this properly, let me just give you an example. Let us say that this is the circumference of our nanotube, this circle over here. So the wave function would basically be spread throughout this entire surface. So it looks somewhat like this. So here, this one, let me just redraw it. So it's actually a sinusoid, although it doesn't look like one. So now here, let us say that the wave function, if it goes like this, and then there is a discontinuity, so this wave function just abruptly drops here. So this basically violates the principle of quantum mechanics, that it should be continuous. Okay, and the second thing is that this is not a stable state, because the wave function cannot, if the wave function changes abruptly like this, the derivative would also be discontinuous, and there would be a discontinuity in current, if any. So this kind of wave function is not possible, rather it has to be continuous, so it has to go like this. Okay, so at any point if you look, let us say if at this point if you look, once the wave function completes one loop around this circumference of this cylinder, it should go to the same phase or it should go to its same value. Okay, so that is why this product should be an integer multiple of 2 pi. Okay, now for a zigzag nanotube, the direction along which forms the circumferential direction of the nanotube, it is basically this direction over here. So we can call this direction as let us say C equals to so let us actually write the circumferential direction over here. And this was basically equal to 3 by 2 a0 m plus n x cap plus root 3 by 2 a0 m minus n y cap. And if you remember, this part we called as a, and this part basically we called it as b. So this is equal to a m plus n x cap plus b m minus n y cap. Now what is the condition under which this circumferential vector is directed along only along this y axis over here? So of course this part must be 0. If the circumferential direction is along this axis, okay, we will call this axis as y axis basically. So let me write it here. This is our y axis, and let us say that this is our x axis over here, because that is the way we chose our lattice translation vector. So if you look at this diagram over here, you can understand easily that this was the direction of our this was the zigzag direction. Let me just use a different color over here. This is the zigzag direction, and this direction is basically the y axis. So in our later diagram, we have basically rotated this axis and the entire structure by 90 degrees. So basically here we have our y axis to be in this direction and x axis to be in this direction. And this is important because the y and x direction are not equivalent here. And this is the way that we have chosen our lattice vectors a1 and a2. Okay, with this orientation with respect to the graphene nanosheet. Okay, so now I want my circumferential vector to be in this direction. Okay, along the y direction only. Okay, then what should be the relative values of m and n? So m should be equal to minus n for this to be equal to 0. Only then the circumferential vector would be along the y axis over here. So we basically put m equal to minus n. So for zigzag nanotube, m is equal to minus n, and the circumferential vector c is basically given by 2b 2bm y cap. Okay, and c dot k is basically given by 2bm ky. Now for the wave vector to exist inside the nanotube, this dot product should be equal to an integer multiple of 2 pi. So 2 pi times v, where v is an integer. Okay, so what do this line give us? This 2bm ky equal to 2 pi v. So this basically gives us a series of lines which are parallel to the x axis. Okay, here actually kx axis actually, because this is defined in the kx ky plane. So here we do have a series of lines which are parallel to the kx axis, and each for a given value of this integer v. Okay, so these are basically like subbands for this graphene nano sheet, graphene nanotube. And here we note that this kyb, this is equal to 2 pi v divided by 2m, and we can actually write it as 2 pi divided by 3 times 3v divided by 2m. Okay, now what is the condition under which this nanotube would basically show a metallic property? So when I say metallic property, this basically means that what is the condition under which this carbon nanotube, this zigzag carbon nanotube basically shows no band gap. Okay, so we know that the points in the Brougham zone, or in other words the k points for which this graphene nanotube does not show any band gap, not graphene nanotube but graphene nanosheet. So the points in the Brougham zone or Brillouin zone for which graphene nanosheet does not show any band gaps, these are basically kxa equal to 0 and kyb equal to plus minus pi by 3, kxa equal to pi, kyb equal to plus minus 2 pi by 3, and kxa equal to minus pi, kyb equal to plus minus 2 pi by 3. Okay, so for this one, for this zigzag nanotube to be metallic, we should have this kyb equals to 2 pi by 3 for a given value of this subband v over here. Only then one of this straight line over here which corresponds to a given subband, only then this would basically pass through this point at which there is no band gap, that is this point over here. So one of the subband would then pass through these points. Okay, in that case this graphene nanotube, which is zigzag in nature, would not show any band gap. Okay, so if this kyb has to be equal to 2 pi by 3, in that case this one has to be 1. Okay, so what do we need here? Now v can be any integer. Okay, in this carbon nanotube v can be any integer, and for a given value of v we would basically be having one subband. Okay, v does not have any restriction. The only restriction that we have is that v should be an integer. Okay, so since v can assume any integer value, therefore the only condition that we have to satisfy to make this entire thing equal to 1 is that m should be an integer multiple of 3. If m is an integer multiple of 3, then this entire thing can be 1. Okay, for example, let me give you an example over here. So let us say if this m is equal to 33, in that case this 3 and this gives us 11, so we have a 2 over here, so this denominator becomes 22, and then for v equal to 22 this entire thing becomes 1. Okay, so I repeat again that if m is equal to 33, then if m equal to 33, then for v equal to 22 this entire product becomes 1, and one of the subband in that case passes through either this k point over here for which there is no band gap, and this k point over here for which there is no band gap. Okay, similarly we can have other conditions for which the one of the subbands basically pass through these k points over here. Okay, that condition can also be satisfied so that this carbon nanotube is metallic. So this is how you basically check that how to make a carbon nanotube with metallic property, and then if you also want a carbon nanotube with semiconducting property which basically has a band gap, then you can also make a carbon nanotube with semiconducting properties by making this m a non-integer multiple of 3. Okay, if you make this m a non-integer, or if you make this m uh, or if m is not a multiple of 3, let us say that m is equal to 11, in that case we really cannot find any value of v for which this entire thing is equal to 1. Okay, so by careful calculation and by judicious choice of this, not judicious but by a clever choice of this m over here, we can basically make either a metallic carbon nanotube or a semiconducting carbon zigzag nanotube. Okay, so similarly we can have also armchair nanotube. So for an armchair nanotube, this is the axis of the hollow nanotube, and the circumferential vector which forms the circumference, or the direction which forms the circumference of the nanotube, lies along this x direction over here. This is C. And just to remind you, according to the axis we have chosen, this axis is our y axis and this axis is our x axis. Okay, so here again C is equal to m plus n a x cap plus m minus n b y cap, and then to make this circumferential vector C only along this x direction, what we have to do, we have to choose this m equal to n, so that this part is basically 0. Okay, so for an armchair nanotube, m is equal to n, and for armchair nanotube basically this line is basically exposed, and since it looks like an armchair, that is this one, since this line over here looks like an armchair, we call it basically an armchair nanotube. Okay, so if m equal to n, this C is equal to 2m a x cap. Okay, and then this C dot k is equal to 2m a kx, and this one, for the wave vector to exist inside this nanotube, this product should be an integer multiple of 2 pi. Okay, again v is equal to an integer over here. So this product kxa should be equal to 2 pi v divided by 2m. Now we again come to this 6 points at which the energy gap is 0, the 6 points over here, and we note that this for kxa equal to 0 and kyb equal to plus minus pi by 3, we have one point where there is no we have one point in the Brillouin zone or Brillouin zone for which there is no band gap. And now if we look at this expression over here, we note that for v equal to 0, this kx a is equal to 0, and so because v can actually assume any value, okay, for each value of v basically gives rise to a particular subband. Okay, so we can assume any value provided that the value is basically an integer. So we note that for V equal to 0, this Kxa would always be 0, and therefore because we can assume any integer value or we can take any integer value, therefore one of the subbands would always pass through this point. So one subband will always pass through Kxa equal to 0, and this is exactly the point at which there is no band gap for carbon nanosheet. Okay, of course you have also this value ky b equal to plus minus pi by 3, but note that this equation over here gives no constraint on ky, so ky can basically take any value. Okay, so ky can basically take any value, so that is why this point ky b equal to plus minus pi by 3 is also a valid wave vector for this armchair nanosheet, for this armchair nanotube. So, and because for v equal to 0, one of the subband would always pass through this point kxa equal to 0, therefore this armchair nanotube always displays a metallic property. Okay, so armchair carbon nanotube will always have metallic property. Okay, so this diagram basically shows the different lines for each of the subbands of armchair carbon nanotube in the Brougham zone of this graphene nanosheet, and each of these lines basically correspond to a given subband, and we note that there is always one line that passes through these points kxa equal to 0, and hence this armchair nanotube would always display metallic property. There is no band gap in case of armchair carbon nanotube. Now this image on the right basically shows the dispersion relation for graphene, and these are exactly the special points at which the band gap is 0, and these are the 3 points over here, and 3 points are one point is over here on the other side of the diagram, one point is right here, and another point is somewhere around here. And note that we do not need all this detailed relationship or all this detailed EK diagram for electronic devices, but it is actually sufficient if we approximate or if we know the EK relationship for graphene or the energy versus K vector relationship of graphene around the points at which the energy gap is basically 0, that is this point, and this point, etc., because that is the point or that is the regime which determines conductance, electronic properties, electronic transport of materials. Okay, and this is exactly the energy at which the Fermi energy also lies. Okay, so the Fermi energy lies exactly at this energy over here, or at this energy, or at this energy. So these are all the same energy points, and the Fermi energy lies exactly at the point of intersection of this conduction band and valence band. So if we talk about conduction band and valence band of graphene, this upper part is basically the conduction band, and this lower part basically constitute this valence band. Okay, and this diagram at the right basically shows the zoomed in diagram, and this is again the bottom of the conduction band, and this is the top of the valence band, and it is actually sufficient to understand the dispersion relation or the energy versus K vector relation around this region over here, which determines most of the properties or most of the electronic properties for semiconductor devices. Okay, also the Fermi energy lies exactly here, which is basically the point at which the conduction band and the valence band touches each other. So the Fermi energy lies somewhere around here. Okay, so it is similar to saying that when we model silicon, or when we want to know the electronic properties of silicon, it is sufficient to know the properties of the minimum of the conduction band or the properties of the top of the valence band. Okay, whenever we discuss about common semiconductors, for example silicon, germanium, we do not really worry about the entire band structure in the Brougham zone or Brillouin zone, but we just try to understand the properties like effective mass, relaxation time, etc. at the bottom of the conduction band or at the top of the valence band, because those are the regions in the band structure that contribute to the electronic properties of that material. Okay, so to model or to know the relationship or the simplified relationship at the top of the valence band or the bottom of the conduction band in graphene, we just take our usual relationship that we have got by calculation. So let me just write it here. So we had this relation E phi 0 equals to 0 H0 H0 star, where H0 star is the complex conjugate of this H0, and 0 phi 0, where phi 0 is a 2 cross 1 vector that contains the wave function at the eighth lattice point and the bth lattice point. Okay, and H0 was precisely minus t 1 plus e to the power minus I a1 dot k plus e to the power minus I a2 dot k, which again we simplified this earlier, so I am not doing the calculation right now. So this is equal to minus t 1 plus 2 e to the power I kx a cos kyb. Okay, now we know that this H0 is equal to 0 at kxa equal to 0 and kyb equal to plus minus 2 pi by 3, and these are also the points at which the conduction band minima meets with the valence band maxima. Okay, so to develop a relation near the bottom of the to develop a dispersion relation near the bottom of the conduction band or the top of the valence band, we basically have to expand this expression in a Taylor series around this point over here. Okay, so how do we do that? So we basically write H0 as approximately equal to kx del H0 del kx at kxa equals to 0, kyb equals to plus minus 2 pi by 3 plus ky minus plus 2 pi by 3, 3b actually, because kyb is equal to 2 pi by 3, this means ky is equal to 2 pi divided by 3b over here. So minus plus 2 pi divided by 3b del H0 del ky kxa equals to 0, kyb equal to plus minus 2 pi divided by 3. Okay, now del H0 del kx, this is equal to minus 2 I a t e to the power I kxa cos kyb. We are basically evaluating it at kxa equal to 0, ky b equal to plus minus 2 pi by 3. So if we put kxa equal to 0, this factor goes to 1, and if we put this this kyb equal to plus minus 2 pi by 3, this entire factor basically becomes 3a0t divided by 2, and we put a I over here, where I is basically denotes the square root of minus 1. Okay, so this is a complex number basically. This 3a0 by 2, this part is equal to a. Okay, so we can also write it as let me rub this part, I a t. Similarly, del h0 del ky, this is equal to 2 bt e to the power I kxa sin kyb kxa equal to 0, kyb equal to plus minus 2 pi by 3. Okay, again if we put kxa equal to 0, then this entire factor goes to 1, and then if we put this plus minus 2 pi by 3 in kyb, this entire factor in that case basically becomes plus minus 3 a0t divided by 2. And again if we want to express it in terms of b, because this derivative is with respect to ky, so if we want to express this in terms of b, this would basically become plus minus root 3 bt. Okay, so if we expand the entire form of h0 around this point, we would basically get kx sorry, del kx plus ky minus plus 2 pi by 3b del h0 del ky kxa equal to 0, kyb equal to plus minus 2 pi by 3. Okay, so this is equal to I, where I is equal to square root of minus 1, 3 a0t sorry 3 a0t divided by 2 kx plus, we actually have a plus minus sign over here, so we have this plus minus ky minus plus 2 pi divided by 3b. We actually have a I over here, because in the earlier case this was imaginary but this part was real, so we have to put an I over there, and if we put a I over there, I square is minus 1, so this would become minus plus. Okay, and we call this part as beta y, so I 3a0 t divided by 2 kx minus plus I beta y. So this is the approximation of H0 around the point this kxa equal to 0 and kyb equal to 2 pi by 3. Now we know that the energy E, this we have done earlier, so I am not repeating those steps again. So this is equal to plus minus mod of H0, which is equal to plus minus 3ta0 divided by 2 root over kx square plus beta y square, and this beta y is nothing but ky minus plus 2 pi by 3b. So we note that this locus of E, the locus of this kx and ky is basically a circle for a constant value of this energy E. So the constant energy contours in the case of this carbon nano sheet or graphene or carbon nanotubes are basically circles inside the Brillouin zone or Brougham zone. So this figure basically shows this constant energy contour. So if we travel along this circle, we would find a constant value of this energy E. Then the second circle we would also find a constant energy E, but this energy of the second circle is slightly greater than the energy of the first circle. And similarly the third circle, if we loop around the third circle, we would also find a constant energy E, but the energy of the third circle is basically greater than the energy of the first two circles. So we would find a constant energy contours if we plot the constant energy lines for graphene. Okay, graphene or carbon nanotubes. So the constant energy contours of carbon nanotubes or graphene or carbon nanosheets are basically circles. Okay. Now another fine thing to note is that if we basically denote, if we basically define a new wave vector along the k direction, along the y direction or along the ky direction by this term beta, where beta is basically ky minus plus 2 pi by 3b, then this energy is nothing but this is plus minus 3ta0 divided by 2 k. Okay, capital K, let us define it, where mod of k basically. Okay, where this capital K is basically, let me just go back to our previous image, a vector centered at this point over here. Okay, let me use a different color, use black. So centered around this point over here. Okay, so k may be the magnitude of this vector, capital K that is, or capital K may be the magnitude of this vector, or capital K may be the magnitude of this vector. As long as the magnitude of this capital K vector is the same, we basically have the same energy. Okay. So this capital K vector is basically defined assuming that the origin is basically, let me write it here, capital K is defined assuming the origin to be kx equals to 0, ky equals to plus minus 2 pi divided by 3b. Okay, so we note that the dispersion relation at the point of or at the junction of the conduction band minima and the valence band maxima is basically linear with the magnitude of this k vector defined with this new origin over here. Okay, and if the energy is basically linear with the k vector, then the effective mass then the effective mass which is basically defined by m equal to h cut square del 2e del k2 inverse. Of course this is for isotropic effective mass. Okay, this is equal to 0 for graphene near the point of junction of the conduction band minima and the valence band maxima. Okay, so yeah. Okay, so let us do up to here today. We are now almost ready to go into the transport part. So thank you everyone.